Manufacturing Hub. We have a very special guest, Colm Gavin, who we will go ahead and introduce in just a minute. We had Colm on all the way back in episode 42, and it was an awesome conversation. And we've had a number of offline conversations that you guys may or may not have seen about simulation in the past. And so this month, as we are jumping into answering the question of what is Industry 4.0 and talking about practical applications, Colm was at the very top of my list of, hey, let's go talk about simulation. Let's go talk about digital twin. Let's go talk about the applications that would translate into that. Before we jump in, if you guys are new here, welcome. If you've been here before, welcome back. Every month we pick a theme. This month in January of 2024, we're talking all about practical applications of what is Industry 4.0, and we're having 3 different conversations surrounding that. If you guys are new here, we do our very best to have a super active chat, so please feel free to go ahead and drop comments in there. We will do our best to go pull chat in there, assuming you guys have questions and assuming that we can go see the questions on LinkedIn in our restream real and in time, which sometimes we have issues, although I now see like a dozen comments from Vlad as we were jumping in. And Daniel, thank you for being here. And so if you guys have questions, please feel free to go ahead and drop them in. If you guys ask super technical questions or we don't have the opportunity to get back to them, we will do our very best to go ahead and get back to them after the stream. But without further ado, everyone, welcome to Manufacturing Hub. This is episode 150. We'd like to re-welcome Colm Gavin of Siemens back on to the show. Colm, thank you for being here.
Thank you, Vlad. Thank you, Dave, for having me. Pleasure.
Thank you so much for joining us today and taking the time, Colm. Before we dive into maybe the technical aspects of digital twin and simulation, could you give us a bit of a recap of your background? Ultimately, how did you get started, I want to say, in manufacturing, and what are you doing today with Siemens?
So Colm Gavin, I'm part of the Siemens Digital Enterprise team, where we focus on our hardware and software solutions working well together. Simulation, virtual commissioning is really the key part of that. I've been with Siemens since September 2000, so almost 24 years. So people joke I'm institutionalized at this point. So no, it's been a great experience. But my background was manufacturing engineering from university in Ireland, and worked for a systems integrator. I worked for packaging OEM, and then of course worked for Siemens since 2000 on a variety of different projects. I spent most of my career on the automation side, application engineer, PLCs, drives, supporting large customers, machine builders. And then in 2006, I had an opportunity to go to Germany to work on the development of our next generation automation software, which is our TI portal software. So I was involved in the development, the usability of that. Spent many years in Germany. I've a lot of time invested in that software from my side. And then returning from Germany, then looked, once the logical next step was looking at our PLM, our design and simulation software, because as you know, Siemens, from our accelerator platform, we are continuing to integrate our design, simulation, manufacturing, automation tools together. So I'm over on our software side now, but working closely with our automation colleagues where our hardware and software tools work well together. And that's design, simulation, IoT, all of that, if you like, kind of as Industry 4.0 has developed, these new technologies have evolved. But simulation in this case for sure has been, I think I mentioned it to both of you before, I believe is the most mature, if you like, of the Industry 4.0 topics. Siemens has invested in for many, many years through acquisitions, a huge amount of billions of euros, dollars into the development of our simulation, whether it's machine, robotics, plant level, physics, deep level physics simulation. There's many different areas we've invested in for machine builders and end user manufacturers as well in a variety of different industries, automotive, aerospace, food and bev. So it's a great topic. It's exciting to be part of because I think these technologies are just getting better and better. And now we've got the industrial metaverse, which is taking it to the whole next level, right?
And I'll say, Colm, on that side, I really appreciate the fact that I think you have a very diverse background before getting into simulation and digital twin, because I think that encompasses so many different aspects of manufacturing that I think having, you know, those experiences on like PLC, HMIs, SCADA systems, manufacturing is really important, again, to see sort of the bigger picture, right? That is not just
Well,
purely.
I think, right. I mean, I've been on plants before. I'm not going to name names, but where production rates, a major product is launched into the market, and there's a date set in stone when that product will go into stores, and everything works backwards from that launch date of that product when it's in stores. So they had to produce X number of millions of products, if you like, that had to be in the stores on a certain date, because that's when the advertising and everything, the market, the promotional for that. So working backwards from that timeline, that's when we have to design the systems that have to be implemented and produce the products. And of course, that time gets crunched. And so I was part of those, I'm an automation engineer by trade. So we're usually the last in the line. We're at the end of we're trying to debug our code, and we've got a launch date we have to hit. Mechanical still not finished, and we're stuck in the middle trying to prove out the code and get it done before the launch date. So let's just say I have the scars on my back that when I saw the simulation and the virtual commissioning, it resonated with me very clearly that if I had those tools available much earlier, they would have certainly have helped us prove out, let's say, mechanical designs that maybe weren't fully vetted. Controls engineers have to come up with the workaround to make it work. So,
and let me, I guess, ask a fairly fundamental question that I think will reflect on someone who's maybe not familiar with these tools. And I think there's an important distinction to be made between, let's call it digital twin, and then I want to say virtual commissioning or simulation. And I think simulation has certainly gone a very long way, right? And we'll get into that conversation also. But how do you maybe define when you say simulation or virtual commissioning versus what digital twin offers? Like, how would you?
Yeah, it's sorry. There's a lot of jargon that we have in the industry right now that's maybe it's confusing for people. You can ask 10 different people what a digital twin is, you'll get 10 different answers. So a digital twin, if you like, can be as simple as a 3D CAD model is a digital twin of a machine or a process. It really comes down to your use case. If you have a data model coming off machine, people might say, well, that's a digital twin of the data coming off. So it's very abstract. So from a Siemens perspective, we approach it like from, let's say, a comprehensive digital twin, where we look at, say, the 3D model, the electrical drawing, the automation, and also, let's say, the backbone, the PLM backbone to kind of manage all that data. You could look at that as a digital twin, like we refer to that as a comprehensive digital twin of combining all of the different the data sets, if you like, that go into making a product, electrical, mechanical, CAD, and so on. And controls. So that's kind of a bigger picture. Different people might have different definitions for what exactly is the digital twin. I mean, essentially, it's a virtual representation of a physical asset, right? And so, is it a CAD? Is it electrical? Is it just pure data? That's where maybe the devil's in the detail. But essentially, it's a virtual representation of a physical asset. Simulation, of course, is where we can, and even simulation itself, you can look at it in different angles. Simulation of a machine, simulation of a robotic cell, or simulation of a complete line or a plant. Those are different tools. Let's say addressing different use cases. If I'm designing a product, do I care about the design of the physics of the product itself, or am I designing equipment to make the product? So I have a digital twin simulation of that. And then, of course, once it's in operation, then it's all about the IoT, pulling data out of that. Some people refer to that as digital twin of performance. So I think in this conversation today, maybe from an automation perspective, you're really trying to combine, you've got your CAD modeling world, and there's different models addressing different use cases. And how do we connect that with, how do we prove out automation logic against that? Virtual commissioning sometimes is towards the tail end, what we refer to as let's say, a digital thread of where you start with requirements, you have your layout, you have your design, there's the build, and then at some point, you want to prove out, as we define virtual commissioning, is proving out automation logic against a virtual representation of that machine. Now, if you look at the machine, say at the machine level, you can break that into maybe two different distinct areas. One is what we refer to as, let's say, a system level model. So let's say I have a machine, and again, you'll hear me use this word a lot, use case. Use case, use case, use case. And that's so important when we think about simulation, because you're always trying to find what is the sweet spot of the amount of extra work. Yes, it's extra work to develop a model and a digital twin. What is the amount of effort, or what should I do to address the use case that I have? So if I'm developing systems and I don't necessarily care to see, let's say, a 3D representation of the machine, my use case is, are my motors are sized correctly? What about the temperatures, or the hydraulics, or the vibration? Let's say the system aspects of the machine. That's a digital twin right there. There's a whole host of companies, including Siemens, can provide, let's say, 1D modeling software where it's I'm modeling the physics of the component, the fluids, the temperatures, the pressures. That's a whole level of simulation. And I think a great one, maybe concrete example, we were involved in this for many years, is, hydraulic simulation. If you can imagine, when they were developing aircraft, they wanted to simulate the hydraulics controlling the wings, right? So that's like I don't necessarily need to see them going up and down. I need to really see the pressures and temperatures and timing, and is that measured correctly? So that's a system level simulation. Then we have, let's say for machine builders, especially where automation comes in, and you could argue, well, that's very much a mechanical design, right? But if I want to prove that out, how the components are sized correctly, I may want to tie my automation logic into that, and so we can do that at a system level. If I have a more common use case of, okay, I've got a 3D model of a machine, let's say a packaging machine or some material handling type machine, and my use case is, I want to verify, how is that product that's moving through the machine, how is that product behaving? Will it jam? Will it tip over? What are the physics associated with that product? But I need a CAD visualization of the product moving through the machine, and I'm going to use that then to prove out my automation. When it hits a sensor, fill it, pick it up, move it, whatever you have to do. So I'm turning on actuators, and I'm looking at sensors, the PLC code is reacting, but I need that CAD visualization. So that's a use case. And then you can get into, say, robotics programming. Let's say we all know that when we talk about automation, especially, say, in end user manufacturing, when they look to automate a process, we're going from manual labor and maybe putting many cases you might see a 6-axis robot going in, palletizer or pick and place, doing something, FANUC, ABB, KUKA, 𝐒𝐢𝐭𝐦𝐿, all of the 𝐒𝐢𝐬, different universal, if you're working with those 6-axis robots. And that's another virtual commissioning use case, because that's maybe a very common one that we're dealing with. And I want to prove out, I'm going to program the robot, I want to simulate the robot, but I gotta program and simulate everything around that robot that a PLC would control, the guarding, the material handling, everything that's around that. So I've got robotics programming and automation programming. So that's a digital twin simulation that we can think about. And then stepping back, there's a whole other level of just, well, I don't care about the physics, I just care about throughput, bottlenecks, and I want to maybe coordinate, let's say, a line integrator, system integrator. I need to simulate, material handling, large scale systems. How do I validate the code that is controlling the interaction between them? Traditionally, maybe a line controller, right? You'd have a line control PLC is maybe feeding signals. It's getting signals from subsystems, and it's coordinating the interaction, the handoff between those systems. Well, that's a whole level of simulation and virtual commissioning, proving out the automation code against that. So, not long-winded answer, I know, for different areas where simulation, so virtual commissioning, in essence, proving out that automation code against a model. What model is your use case for what you're doing?
Cool. Let me throw one last question at you before I pass the mic to Dave, as a follow-up to that, because I think what I at least see with the end users that I talk to is that I think there's so many options, they maybe aren't necessarily sure what the lowest hanging fruit is. So I'm curious if there's maybe a model that you use when you approach the maturity of an end user and sort of suggest based on their current state what they should be looking into, or it really is as open, as you've described all these different use cases? Because I think you can go extremely in depth into each one of those, right? Even the package handling use case, I'm familiar with that because you can even pretty much program the physics of the materials, right? And there's like a whole science in how that's going to be handled. So you can
Correct.
go extremely in depth, right? But is there maybe hey, if you don't currently simulate, if you don't currently do any virtual commissioning, maybe that's the first kind of step. And as
Yeah.
you
Yeah, I mean, I think maybe I mentioned it that the most common one that we're seeing right now is around robotics, integrating robotics into lines. If I'm an end user manufacturer, more than likely, if I'm looking to automate a process, then I'm going to put a 6-axis robot in there because the cost of those robots have come down. Sometimes those robots are embedded in machines that come from a machine supplier. Sometimes it's the system integrator will put in a robotic cell doing pick and place, and many times then maybe you have 2 or 3 robots working together. So I think that's where we're seeing, let's say, if you want to start, if you like, and that's to answer your question, robotic integration and line integration of those robots in. And so that's an area to start if you're looking to go from manual to automate something. And then, so how do you program that robot? How do you train it, teach it the paths? And then how do you prove out the automation logic around it? That's maybe one of the examples I was going to show later here today as well. So
good. So we'll definitely dive into that. Dave, thoughts?
Absolutely. Colm, I was going to say, I think you gave a lot of kind of interesting topics in talking about how digital twin depends upon use cases, and you kind of shared a number of those use cases at kind of a medium to high level. Do you perhaps have an example of a success that you can share, either that you've been involved in or perhaps a Siemens Solutions partner has been involved in, to kind of tie everything together for the listeners at home who are trying to understand maybe some of the more practical applications of the simulation and digital twin, please?
Yeah, I mean, we've done digital twin solutions for machine builders, for some packaging applications. I mean, some of the slides I'll show you here in a moment, I can pull up some examples. I can reference some particular customer references that are in there. I think where we're seeing for sure, like at least in the US, automotive and aerospace, definitely automotive, as you can imagine, they lead the charge in this. They are, say, the most advanced vertical in this. So I've heard somebody say, one of our machine supplier, or one of the system integrators we work with in the US, that I think this is true, but maybe 50% of automation in the US is automotive related, right?
Okay.
Feeding systems, if you think about it, right? The line integrators, the machine suppliers into all the different automotive companies, and now we have batteries, the gigafactories, switching to EV. If you can imagine, there's a huge amount of automation associated there. So I think that's where we have maybe the most applications, where the industry that's further along is around automotive, and where they are beginning to make it part of their requirements, their specifications, digital twins, models they want as part of the milestones from their line builders. They want to see the models, they want to verify it. Sometimes they have third-party companies look at the models, sign off, yes, this is exactly what it's going to do, so that when the systems show up, and these be complicated multiple robot systems, where they really have to make sure there's no collisions and this sequence of operations are really proven out together. And so they want that, and they want it maybe even from like some smaller system integrators and some of the bigger integrators as well. So I think that's where without getting into customer names because of NDA and whatever stuff like that, that's automotive is probably where we've seen they're furthest along. But we are beginning to see other industries, electronics and food and bev as well. Some food and bev begin to look pharmaceutical as well. The growth, and this maybe goes to one of the questions you had, I know, is like, okay, what's the expectation, the life cycle of a digital twin, or the future of a digital twin? And we see that more and more, where large end users who may want to take some IP back in-house for what they're doing.
Okay.
We've seen that as a use case where they are now, look, if we're going to take the IP back in-house, and we want to, because maybe if we've been too reliant on some of the machine builders, that they or even, again, better validation, virtual training an operator, because that's a great use case. We talked about this, Vlad, before, right? Let's say, well, apart from obviously, the why would you have a digital twin? The virtual commissioning is to a variety of reasons, right? So primarily it's reducing the cost, reducing the risk of the physical equipment when it's in. So everything works as expected. So reducing the damage, obviously mechanically, but also reducing the commissioning time, the startup better, safer, more confident startup times that everything's going to work. So the really reducing the cost. But then, of course, you have once you have it, then you have the training opportunity, because you can do a virtual HMI, virtual PLC and the model, or you can do a real HMI connected to the virtual PLC and the model. So training. So end users are really like, okay, how can I train an operator to use this machine before they really let them loose on the real thing? Crash the machine all day long in the virtual world, but train an operator correctly so he can use it. And once he's out there, we see a lot of use cases where people are using it for promotional marketing. So machine builders, like if you're an end user and you put a bid out for, say, a processor or a machine, and you have machine suppliers who come back, if the machine suppliers come back with a digital twin that can really show you exactly this is how it's going to work, this is the use case, and we're maybe seeing that as well, where end users maybe want more collaboration with their machine suppliers. What is the sign off? You have this term, let's say, a virtual factory acceptance test. I mean, you'll never get away from a real factory acceptance test. You always will need that, of course. But how much can be done virtually ahead of time? And really, the end user knows exactly what they're getting. Because I've heard that from other end users, different industries, where the machine supplier here's the equipment, they show up, here's the documentation, they're maybe there for a week or two deploying it, and then they're gone. And then the moment a month later, something's wrong, nobody knows how to fix it. Mm-hmm. So the end users I think that's going to drive more adoption, where end users they want these models for a variety of reasons: training, understanding, validation, sign off. And in some cases, they want the IP for what they're doing in-house. And there's a collaboration, then they have to work with their machine suppliers to help them to design it, because they may not have the capability, obviously, to design the machine themselves, but that's different ways we see progressing.
And Colm, if I can follow up on that, and I guess I'm not as familiar with the automotive industry, but I know at least with robotics in palletizing in food and bev, there's always the pressure, I guess, the opportunity to optimize robots as well. So I'm assuming that the long-term play after it has been deployed, you can also simulate, or I guess create a digital twin that would allow you to increase the throughput of your line, or see where there's like opportunity to, I don't know, either like gain some movement speed on the robots or optimize.
Of course, absolutely. And I think maybe you hit on an important point there. Let's assume you've developed a digital twin of a robotics system or a line, and then you have your good idea, a baseline for throughput times and so on. Very often it's important when the system is actually installed that you go back and calibrate the model against what physically is on the floor. So, the throughput time, maybe in the model it thought it was 10 seconds, but actually in reality it's 12. Okay, so there's a variety of different ways with Siemens tools, at least, where we can calibrate the model once it's in operation. That's really important, because once you have that, now those, what if scenarios. What if I change something? What if I add another robot, or I need another line? Those what if scenarios that are really difficult to do on a running system. This is where the having an accurate, calibrated model can really, really help. And then we see some companies, the next development of this is these tools moving, which say they were born in the design world at the early stage, but once the machine or the factory or the warehouse, once it's in operations, how do you then, if you've gone to the trouble of developing a model, especially of the line or the whole facility, using that in operations for what we refer to as closed loop digital twin, closing the loop, so that if you haven't, we've used this term like an always on closed loop digital twin that's kind of constantly reacting. And warehouses and distribution are a great example of that, where maybe you don't know you're not making the same thing, and maybe your incoming orders, depending on the time of the year, you get a crazy order, like, okay, how does the system need to adapt to handle these unexpected orders coming in? So if you have a calibrated kind of always on digital twin that's giving you, say, recommendations, depending on who showed up, labor utilization, machine utilization, and then critically as well, another aspect that we're finding, and we've developed tools to help with this, is that who's using the simulation tool, who's going to use it, and who needs the benefit from it. Very often we're seeing that, okay, if you have a simulation engineer, industrial designer group, they will develop the model, maybe a combination of mechanical and automation, whatever, they'll develop a model. But then once you're in operation, how do you ensure that, let's say our plant simulation software, for example, where it can give really good recommendations, if the shop floor operations, they're like, I know I have a problem. I know I have a bottleneck. I've got 10 different dashboards that tell me I've got a problem. Give me a recommendation for what I should do. That's so the predictive simulation software, something like for a plant simulation in that use case, can give that. But not everyone's going to get in there and click around and do that. I'm a shop floor operator. So we've provided, let's say, web-based tools to allow basically a custom user interface that is an in-between that allows, give somebody the ability to say, easily enter in a shop floor operator, just a couple of key parameters that's important for them, run the model. I don't even know what it looks like, but give me the answer back, and then I can react on that. So it's kind of providing users a way to interact with simulation software with a custom GUI web-based tool that's running the models in the background, but give me something back that's meaningful for my role. Could be a management, could be shop floor operations. And we use this term that can really help democratize simulation software. Who actually is going to use it? Who's benefiting? Who wants the results from it? I think especially like in manufacturing, end user manufacturing, where the type of simulation we're talking about here is a line level plant simulation where throughput, KPI, bottlenecks, machine utilization, labor utilization. When you get into those scenarios, you want being able to adapt to that on a kind of on the fly, continuously on closed loop digital twin. That's great, but you got to give away maybe an easy way for people to use that. And we've developed tools to kind of interfaces, web-based tools to help people. They don't have to be experts to use the tools to benefit from the results of the tool. I think that's going to be a key thing as we go forward. More people can get the benefits from what the tools are doing.
Dave, thoughts?
Absolutely. So I love what you're saying, Colm, and so does almost everyone in the comments. So we've got a couple of comments, a number of comments that I want to make sure we highlight, and I'm going to mostly go backwards because I think all of them brought up some really good points. So Johnny talking about how he thinks when most people hear digital twin, they think of like a 3D model, when in reality, it's the system modeled in the data. And Colm, I think you made a really good point about that. And we had asked in the chat, has anyone gone and has been using digital twins? And Marcus is in the chat talking about a previous employer that did a retrofit as the first step of a digital twin. Maybe not the best choice, especially with something with fluids such as hydraulic and pneumatic. And then Marcus was also talking about how they had issues with updated systems that were faster than the old PLCs, and the slower cycle time hid some of the issues that came apparent only after performing the upgrade. And I think that's a really interesting point that you hit, Colm, and I want to perhaps go back to it because in all of the conversations that Vlad and I have had with a lot of people surrounding digital twin, I'm not sure we've ever heard someone say, hey, after we build this, we have to calibrate it so it's one for one for real life. Vlad, do you remember anyone maybe bringing up that point in some of the previous digital twin conversations? No. So can you maybe hit that one more time for the folks at home, the folks listening, as to we go build the digital twin with the data and the models, and then we have to make sure it's one for one with the actual production process?
Correct. I mean, at some point, right, when the physical machine is built and installed, ideally you've done your virtual commissioning, you've proved out your automation logic ahead of time. But then once the system is running, your cycle times, the faults, let's say, are they random, are they intermittent? any bottlenecks. Basically, the data that you can help calibrate the model. I mean, again, if I just use maybe the example of a line or a plant, you may have multiple pieces of equipment all contributing to an overall throughput. So when the machine is, at the end of an 8-hour shift, did I produce 100,000 parts, or did I ship 100,000 parts? What did I actually do, and how does that compare to what the model did? So you can go back and look at the historical data, what you're able to capture, and then see how close that is. And then you can feed that updated data into the model, because of course, before anything is actually built, you are going to have to you're going to have to enter in baseline data, assumptions as close as you can get for the parameters associated with like each part of the machine in the line. It's energy consumption, it's throughput time, how often does it fault? There's a whole bunch of parameters you can enter into the software. Let's say our discrete event-based simulation software to try to, so when you run the predictions, or when you, because then we can feed parts in, and so you definitely have to go back and calibrate the model, because if you're not, I guess the big message here for me, I'd like to share, or maybe the main message, is that it's wasted effort if you're not using some of these models in operations to help you continuously optimize the running of the system. You're leaving, it's left, you're not getting the most out of the system, especially at end users for kind of those throughput analysis. If you're a machine builder and you're designing a system, and then it's okay, condition monitoring maybe on the machine as well. That's a whole other level. Actually, it's quite interesting topic where we're getting into now, where we've developed system-based models of a machine where we can look at how, let's say, a press, for example, when it comes down and you have mass and force and velocity and speed, all these things, we can model the system. But with some of our system level software, we're able to create, if you like, a reduced order model that we can actually put that running, we're calling it an executable digital twin, where we can put that on a device, and it can run real time to mimic how the machine will run in operations. And then you can use that down beside the machine, and you can have it interact with the machine, and you go, why would you do that? Well, let's imagine you have let's say a system level model of a machine that's really able to mimic the performance and how the machine is able to run. If you're able to do that real time, and you have it, say, down, let's say, on an edge device running beside the machine, a key thing we're finding with some operator or some companies is this idea of, let's say, a virtual sensor. Let's say you have an oven, for example, just as an example, where you can't put a sensor in the middle, or you can, but it breaks all the time, or you can't get an accurate measurement of what's happening. Well, in the model, you can. The model can predict the temperature. And so, or you could create a combination of different things. We're using this for quality control, condition monitoring, where if you take camera data and sensor data, when you combine all these things and you feed them into a model that's running with the machine, maybe the model is able to give some prediction. The model is able to give a prediction for, well, actually, you better slow down or speed up or stop the machine. You're going to have a problem. And then the breakthrough from Siemens in the last couple of years, I know it's not to talk too much about that, but we've been able to deploy those runtime, we're calling them executable digital twins, where it can run real time on a device, we're calling it, say, an edge device down on a machine. And then we can interact with the PLC. So if the model, so the basic workflow is we develop a model, we make sure it's running, it's an accurate simulation for the machine. If we can get a reduced order version of that and put it down on an edge device that can mirror, got my real machine, my model, and if they're running like that, then we can with the edge device, we can communicate to the PLC. So, hey, speed up, slow down, stop, especially where the virtual model is able to predict something that the real machine can't, whether because the sensor is just really difficult to mount, or maybe my virtual sensor is a combination of many things. A data point, a camera data, an input, some sort of something that the control system itself can't really do on its own. Anyway, I know I'm getting into the weeds here now, a little bit of an executable digital twin, but again, the general theme of using models in operation, and I think I've had an executive from a large, say, manufacturer in the electronics industry tell me that, oh, look, I love your modeling simulation for the design side, but our problem is operations. Our problem is I've got a couple of different lines. They're all, the machines are designed the same, but they're not behaving the same. Can I use a digital twin to help me optimize that machine and verify why one machine is not working the same when they're the same type of machine? And there's many reasons behind that, right? But the idea was, how can a digital twin help you with that? And so with an executable digital twin, there's ways there that we can help do condition monitoring, predictive maintenance. Again, it assumes that the model is accurately predicting what the real machine is doing. And then how can you interact with that real machine, do some comparisons, which are virtual sensors, your target set point versus your actual set point. And if the model is able to pick up a deviation, then can you react accordingly? Like ongoing optimization, that's the next frontier, if you like, of digital twin and simulation, is coming out of the my little design world. And nope, we got to find uses for these in operations. So
I certainly have a lot of, I want to say, thoughts and ideas on different use cases looking back at some of the initiatives I worked on. But Cole, maybe to bring us, like taking a step back to what it requires to maybe create a good, or I want to say a starting point for a digital twin, right? Because I think you've mentioned this a little bit, but I think we all need to also recognize, let's say, as an automation engineer, you're not going to prioritize the same challenges as, let's say, a mechanical engineer, or let's call it a process engineer. And it could be engineer, technician, operator, right? I'm using those terms like a bit loosely, but let's say as an automation engineer, I'm not going to care as much about, let's say, the packaging of the product. I'm going to care about it a little bit, but the process engineer needs to like truly understand that, what materials are going into it, versus, let's say, I'm going to care about the position of the sensors. So I'm curious.
So a very good point. Yeah, let's from an automation perspective, let's walk through, what does an automation person do in regards to a digital twin? What is his role? If you look at the different personas within a company, hypothetically, if you have a mechanical department, an electrical department, or an automation department, sometimes I've seen automation and electrical, the same people. The bigger the company, maybe they have dedicated people doing electrical drawing and separate people doing software and programming. So if you're an automation engineer, you still have to write your code, right? That's, unless you're using industrial Copilot from Microsoft, to automatically generate your code, you still have to write the code. The question is, how do you interface with these modeling software, and which software is most applicable for what you're doing? So the main, if we look at, say, robotics programming, if you like, or even just a package, let's say it's a packaging machine and I'm trying to prove out the automation code there. So the automation engineer, his primary task in this use case is actually defining what is the master list of IO that he needs to define between the mechanical and the automation engineer. So in Nirvana world, we don't live right Nirvana world, but in a perfect world, and this is where the nomenclature, how you're defining your tags, right? Your tag references, nomenclature, tag references, symbol names, whatever you want to call it. In a perfect world, the name that's on the electrical print should be the same name that's in the program. And now, if we're using a model to actually test that against, that tag name needs to be, we're going to use that tag name in my simulation software to drive whatever it is I want to see. So that's really, once that automation engineers clearly define that, because we find that many cases that maybe sometimes exposes not so nice processes within companies. Who's in charge of the references? Who's in charge of the tag names? Does the mechanical engineer define it, or does the automation engineer define it? So the automation engineer, if he, once they agree on who's going to do it, but once they have that master list, he's then basically going to work with the mechanical engineer or robotic simulation engineer as those names, transfer them, because they're going to be imported into the software and used to trigger the simulations that we see, right? So let's say if it's a packaging machine, what we found is that automation engineers, yeah, they can learn the software, they're good, but usually if it's a mechanical engineer who's used to working in, whether it's NX from Siemens or AutoCAD or SolidWorks, whatever it is, they're going to be much faster in, let's say, creating that, say, extra simulation work that has to be done to kind of simulate the machine. So you still have the persona, it's a mechanical engineer, or if it's a robotic cell, maybe this person who's programming the FANUC robot or the KUKA robot, they're going to be the ones still programming those robots using, say, hopefully our simulation software to do that. And the automation engineer, he's responsible for the tags. And then there's a period where the mechanical engineer or the robotics engineer will work to develop the model. And then there's a period where the automation engineer will share that tag list, they'll overlap. Basically, you then do what's known as, let's say, a virtual wire test, right? So you've got your modeling software and your automation software, and you're poking signals from the automation, and then are you seeing the expected result on the modeling software? Did the conveyor move? Did what is
the virtual FAT essentially?
It's a virtual FAT, and I'm going to show an example of that if I have a chance here in a minute. To share my screen, I can give an example, say, of a robotic simulation, and then once the automation engineer has done that virtual wire test, if you like, everything that he's expecting, like his outputs and its inputs, that he sees that expected reaction in the model, then he can write his code and test his code, and then he maybe takes over that. And in some cases, we see that the automation engineer on their workstation, they maybe only have, let's say, a player version of the modeling software. They're not going in and editing the physics-based model or the robotics-based model. They just need to connect to the model, like a runtime version of the model that can import in the signals and can react to their PLC code. So there's a mechanical period, there's a period where they come together, then the automation engineer can kind of just test his code against that model. And then maybe if he sees something, I'm going to crash the part, or the conveyor, the product's not behaving, that's a feedback loop that he can give to the mechanical engineer or robotics engineer to make the correction and then test against it like that.
And he can,
I don't know if that answers your question, Vlad.
No, I definitely really like it, right? And as the automation engineer, you can obviously test the code, and we'll get into that, I guess, simulation in a second, but you can reload the code that you've, let's say, written in the virtual PLC, and we'll hopefully have the time to see how it all ties together. I know you have to break away in not too long, but yes, definitely want to see the demo, Colm.
Yeah, to that point, can I share my screen?
Yes.
I think a picture says 1,000 words, maybe just 1,000 words here. Maybe just share my screen here. 1 second.
Yeah, and I will say it's really interesting, right? Because I think it will change the dynamics and how like automation engineers can also influence some of these builds before they go live.
Yep. So let me know if you can see my screen.
Everyone should be able to see your screen.
So what you see here is on the left-hand side is a simulation software for programming the robots, and that's robot agnostic. So KUKA, FANUC, 𝐒𝐤𝐴𝐵, whatever, with our process simulate software, we can bring those part files in from those vendors into the software. And then we can teach the path, the robot trajectory, the end of arm reach, making sure we're not going to crash into anything. But of course, in this robotic cell, as you can imagine, the AGVs or conveyors or guarding system, that's all controlled by a PLC. And that's where we get into, say, what we refer to as virtual commissioning, is proving out the automation logic. And you can see on the right-hand side, we have a virtual HMI where we have our graph language editor. We're able to visualize that on the HMI, and step by step by step, we can see exactly what's going on. And then when we look at, say, true virtual commissioning, this is where I have my automation logic on the right-hand side, and I can poke signals from the automation side, or I can poke the signal from within the robotic, the modeling software. In this case, you see the robot or the guard door going up and down. And that's, if you like, my virtual wire test, if you like, to verify, okay, that the model is reacting to correctly to the signals that I've programmed. And then I can program the system and so on. And I'll just jump ahead here, in the video. This is where, you can really prove out the automation for an individual cell or a complete line. So that's one example there as well that we can do. Another example that I think, I'm just kind of jumping around here, but I think it's maybe worth sharing is, so this is one that we did for a customer where we have this is a more mechanical level simulation, AG Stacker. This is their machine for the bundle breaker, that the new machine that they brought to the market. And they were really proving out how that the product, they needed that visualization of how their product, as it goes through the machine, how would it behave? and model it accordingly. But then the other use cases here is for training. Here you see you could do a virtual HMI like I showed earlier, but in this use case, they created a real HMI and connected to a virtual PLC and the modeling software running in the background. So this was originally a training station, because many different products would run through this, very different product variations could run on a machine at any given time. So what is the setup? How do you home it? How do you calibrate the machine to make sure that the next product running through will actually run? So there was a training scenario set up there, but then also sales and marketing. They brought this to a trade show without bringing the real machine, and found it an effective way to kind of help promote what is my machine doing. So customers could test drive their product on the machine before they tried it. So those are just kind of some use cases there that I wanted to share that without getting into the visualization. So
it's really interesting. Like, again, I think, looking at this model, for example, even the customer could probably send different models of their product instead of, shipping crates like we've used to, and then be able to.
That was exactly what happened.
Okay.
Yep.
Yeah, that was at the trade show when I was working with the customer. They had customers come in, look at this, see exactly how the machine would run. And one customer, they gave the specifications because they wanted to verify, can my product run in your machine?
Right.
So they gave the specifications to the mechanical engineers who were at the show, and then they modeled it up that night, and the customer came back the next day and they saw, okay, this is your variation of that product running in our machine. Test drive, try before you buy. So it turned out to be very efficient way to help if you're a machine builder, to sell your machine, to promote your machine. So
Absolutely, Colm. I think that this is amazing. I don't know if it was you or someone else that has told us about this AG Stacker application in the past where they brought it to the trade show. I would imagine just bringing that to the trade show and not having to ship the equipment would almost save them more than the cost of the digital twin and simulation in and of itself. So I think that is very interesting.
And that's an important point,
Yes.
right? There's a lot of use cases here beyond the core virtual commissioning, testing out your automation code, your drive logic against the model. Great. Automation engineers, including myself, will lap that up all day long. But the full business value of it, yes, training, sales, promotion, ongoing retrofits, and then the end user, then maybe they want that model, they want it themselves to use for their own training. And there's ways to do it. There's IP on the machine. You don't have to expose that, but you could still help validate how your machine is going to work and the sign off for the end user and so on.
Absolutely, Colm. I think we've got like 100,000 more questions about simulation, but we're going to have to save that for the next conversation we have. We do want to make sure to ask you the kind of finish up rapid fire questions that we ask all of our guests. And the first one, as kind of all of our longtime listeners know, is a question about asking you to predict the future. And I feel like you almost showed us what the future is going to look like, but I'm still going to give you the question, Colm. What do you think that the future of simulation and digital twin looks like?
I think it's just going to grow more and more, especially where you see end user manufacturers are going. That's maybe one area where they're going to push more. They're going to lean on their suppliers, machine suppliers, line integrators, to supply these models to them, not only for better sign off and validation, but if they want to take some of the IP in-house and for their own purposes, they're going to need those models to expand it. And then when they calibrate the models, and they have working models, they're basically they're building up a digital, the library components, if you like, of the digital twin factory of the future for them. So I think that's what's maybe going to be the driver for that. And not every application or every use case needs to be modeled, but for some of the critical ones, whether it's something on the actual product itself, or it's the robotics integration, or it's just ongoing optimization. So I think. So the end users are going to maybe look for it more and more as the products become more available, people become more aware of how powerful they are.
Yep.
And then the ongoing optimization, looking where we once the machine is running, once the factory is running, the closing the loop for ongoing optimization of the individual machine or the whole facility or line, and then democratizing that, giving that to people, giving access to these tools in a way that they can get the most out of them. I think that's something that will really open up let's say more options for that. And then, like I said, executable digital twin, where the model is driving. Think about it, right?
Yep.
The model is driving. Another use case as well I forgot to mention was training AI models. I see, if you think about it, if you have 100, if you want to prove out a machine how it works, you can't waste a lot of expensive products. Well, you could, in a model, you can create synthetic data, you can create the parts that would run through the machine. You can create that and you can prove that out. So I think we have, with an application up on the Siemens, I think it's still up there, the chocolate factory, where we were using AI to optimize the motion control of this line that was kind of coordinating how the chocolate bars were being packaged. So it was truly a motion control application, and they were leveraging AI to kind of optimize the performance of what is the best way for the motion control to kind of package this product. That's not something you can just let loose out on the shop floor. AI to just, it'll break the machine to pieces. So they use simulation as a way to kind of train the AI model, right? I see that as a big use case. Another use case potentially is vision systems. And this is, I think Siemens can excel in this. We all are excelling in this, is to deploy a vision system. Many times you need to stop the line, verify, calibrate the vision system, the quality control system on a line. Well, if you're able to, say, virtually commission a vision system that you're able to use simulation to create the synthetic data, what's a good part, what's a bad part, train the vision system using virtual commissioning, that's another use case. I see actually a growth there as well, where it's too expensive to shut down the line just to calibrate the vision system. In many cases, unfortunately, some of these vision systems, they get turned off because they're too intermittent, they're too finicky. So this is many use cases, but I think long term, I think the end users, manufacturers, will drive the adoption, and the machine builders who are providing these models will be the one who'll survive. I believe, they'll have to over time. So
Absolutely,
I spent many hours battling those vision systems, so I understand the struggle there.
Vlad is the guy turning them off. No, what did someone say? No, we would never say that about Vlad. Colm, we want to ask her some career advice. If someone is interested in getting started with this sort of simulation digital twin technology, what is your best career advice for that?
I think from the automation side, you can start at the basic level, just the virtual PLC and virtual drives and all the electrical components. There's a lot you can do there. I know from a Siemens side, look at what options are there for virtual PLC and simulation of the drives and electrical and the networking. That's really where a lot of, say, machine suppliers, we have them start there and exploring the different tools. So that's, if they want to reach out to Siemens or reach out to other, our sales colleagues to how to help them get started with that. But how can you prove out as much as your automation and simulate your drive logic before you need to, say, connect, let's say, a model to it, where you have those use cases for visualizing the part or simulating system level simulation. So I think, I don't know if that's a good answer for career advice, but I think it's you approach simulation. It's like, okay, how much can you do with the PLCs and drives in the automation world on its own before you need to connect to a modeling software? And then it's the use cases. Is it system level? Is it robotics? Is it physics? The use cases are really important. Otherwise, you'll spin your wheels on it, if that makes sense.
Absolutely. I think that's fantastic. And we do want to be cognizant of time. So last question for you is, who should reach out? Who do you want to go have conversations with? I imagine Siemens is always hiring and always looking for new customers, especially within North America. But who are you looking to connect and have conversations with, Colm?
Well, I think anyone on the call here, reach out to your Siemens sales contacts, and they'll get in touch with the appropriate colleagues within the group, myself, or with many colleagues who are working on this, who can, come and do an assessment at your facility of what you're doing, and give you a roadmap where to get started. We always use the statement: start small, find ROI, find value, and scale quickly. That so with POCs and so on. So we have teams that can help customers map that out, and identify the use cases and what's the priority. You don't have to eat the elephant all at once, if you like. It's bite-sized chunks, and we can help with that. So just reach out to your Siemens factory automation or Siemens software colleagues, and they'll get you in touch with the right team.
Absolutely, Colm. Thank you so much for being here, everyone. Thank you for joining us. This has been Manufacturing Hub, episode 150. If you guys want to watch more, be sure to connect with Colm, Vlad, and myself on LinkedIn, which is where most of you guys are watching this from. Be sure to follow along our pages. And if you guys have made it this far in podcast format, thank you so much. Everyone, please feel free to like and reshare and rate us 5 stars everywhere you can. When we ask and remember to post podcasts, we continue to have numbers that go up and up and up. Until next week, we'll see everyone soon. Thank you. Bye-bye.
Thank you, Colm. Thank you, everyone.
Thank you.